Thank you for the kind introduction, Jenny. I'm happy to be here. This is very much matching my interests, and so I'm glad to share that. As she said, I'm a professor in civil engineering. I specialize in construction engineering and management. And on top of that, my accent gives it away. I'm from Germany, so I'm a German engineering professor, and those three stereotypes overlap, as hopefully will become apparent tonight. Also, yes, I'll be glad to mention Oxford. We can talk about that at the end of the presentation. If any of you feel comfortable showing me your friendly faces, then it's less like I'm talking just to my bookshelf, and also I can see that I don't put anybody asleep, hopefully. That's lovely. Good to see you all. Hi, hi. And so without further ado, let's get to the topic of the evening, shall we? And Jenny convinced me that I'm going to do civil engineering in a non-civil engineering fashion, which is, I will not throw formulas at you, although I will show you one or two just in passing and tell you what they do, but we don't need to actually use them today. The topic for today is something that is very near and dear to my heart, and that is in construction project management. There is a couple of big aspects to how you plan and run a project. And one of these aspects that we'll talk about today is time, okay? Now, formally, this aspect is called scheduling. You all have made a schedule or read a schedule or used the schedule at some point in your lives. In construction project management, we're looking at that a bit more systematically. But today, I just basically want to give you some positive news and some success stories to quench the impression that construction projects always tend to be delayed, which you might very well get if you look into the newspaper. So, Jenny, I wasn't aware that I needed to bring my towel today because it's a Hitchhiker's Guide to the Galaxy or the universe or just the engineering world. But I do have a little bit of guidance and tag you along on a journey as we explore how to build stuff fast. So here's the first case study that we will look at. Anybody know what this is? I will shamelessly pick on people. Caden, can you tell me which edifice this might be?
Is that the Empire State Building?
That is indeed the Empire State Building. Beautiful Art Deco style, unmistakable. And you see here, this is when it was newly built, okay? And you see what an enormous presence it has. I think here this might be a view from Brooklyn over to Manhattan, but I haven't quite found where this the photographer was standing there when they were taking that. Why do I start with the Empire State Building? Well, the Empire State Building is not just beautiful and iconic and the quintessential skyscraper, it is also the fastest ever built. Let's take a look at this and be quite surprised. Let's pick on somebody else. Nick, this diagram has two axes, the blue and the orange one, right? So in terms of the blue axis, this is square meters built per year of construction. And I would say this is probably in thousands or tens of thousands of square meters of footprint. And yes, since it's from Scientific Magazine, we could convert that. And Nick, once I found when I was on an airplane ride that to convert square meters to square feet, just multiply by 10, okay? You're going to be pretty much accurate, plus minus 5%, which is good enough for our purposes, okay? Sounds good, Nick? So you'll find that per year of construction, and I can tell you now that this was built in just over a year, they built about 230, I think, 1,000 square feet per year of construction, which is blazing fast. Pick a few others. Jessica, have you heard of any of the examples here? Name any that you know by name of the other dots.
The Chrysler Building.
Chrysler Building. also in New York City, also Art Deco, I believe, and way lower. You see this, Jessica? It's a fraction. It's less than a quarter of the speed in area per time. You see that? That's quite surprising. Now it gets better. This is probably my favorite chart of the whole presentation, and I didn't make this. I wish I had written the paper that made this chart. Let's take out the orange axis here. And the orange axis is numbers of floors built per year of construction. I told you already that the Empire State Building was built pretty much in 1 year. So we can see that it had about 85, 83, 85 floors in that 1 year that it was built. Anybody got an idea why the others, despite being taller, have their dots much lower? Benjamin? Any thoughts on that?
Hey, Benjamin.
Are you still with us? Otherwise, Sasha.
I'm not sure.
Well, think about this. They are taller. The height has grown, but the construction has slowed. It takes multiple years to build a building nowadays. Okay, so even though they are taller, overall their stats look slower if you divide it by a year. Does that make sense?
Yep.
And the trend doesn't look good. You see that the trend line here from the statistical regression that these authors did actually goes down. So we have a real conundrum. We need to find what they did right for the Empire State Building and how since then, not many skyscrapers in these decades here, but how, ever since the late 60s, we have had a negative trend. Let's find out how this was done. So there's a wonderful book that I happen to have in my collection that you can buy, because there is a notebook from the superintendent of the Empire State Building. And the superintendent described how it was built. Here's some dates. It was built between 1929 and 1931. They started with demolition while they were still finishing their design. They broke ground in March of 1930, and they finished 14 months later. At peak, they had almost 3,500 workers on this site. This was basically employment for, a good part of Lower Manhattan. They built 4.5 floors per week. 4.5 floors per week. How did they do that? Well, this was a structural steel skeleton, so you literally bolt and rivet it together like a gigantic Lego puzzle. Nowadays, you can be glad with concrete if you get to 1 floor per week is the average weekly cycle that I hear when I talk with construction companies, such as, in the Northern Virginia suburbs where I live. They built themselves their own little railroad to deliver the limestone that is cladding the exterior and bring all the other materials in. And you see here how much materials just in sheer volume and quantity was delivered for that. So they planned, I mentioned, right, they built their own railroad to bring the materials to site. So they really made this an almost military style logistics operation. But I don't think that's the secret yet. And what's the secret? Well, they are telling us, I am the kind of scholar that doesn't just teach modern civil engineering. I like to hear the history of things. And so I'm looking at, what do we have here? Well, it's the description of how they organize the construction from a architecture magazine of that year. Here is the magic. On the left, you see a schedule where you essentially see the floor plan, 2 floor plans, one for the lower, one for an upper level, and so you see how the building tapers. And you see an elevation, just a schematic in the middle of the left diagram for what's going on each floor. And then on the right-hand side, you're seeing what they here call a time coordination chart. This is what we will call a repetitive schedule. What makes this a schedule? It's scheduled because at the bottom, do you see that, Benjamin? At the bottom, you have the months, and you go from January all the way to September, and this is for the main structural steel, I suppose, and then they have, you know, the weather enclosure, which is the walls, the windows, that sort of thing, and then they have the interior finishes and mechanical, electrical, and plumbing system. What makes this a repetitive schedule is this. Can you all see my mouse? Yes. So this here is, you see how each of these little steps is basically a repetition of the same task all the way up to the topmost floors. And you see one more thing, Caden, and that is, this is a very, very efficient repetitive schedule. Do you see how these lines are very closely aligned and that they have nearly identical slopes and that they all go basically travel in the same direction at roughly the same slope? That is a hallmark of a fast, efficient, almost factory-like production. And I want you to think of a construction site in a completely new way after this call. Well, talk really after this video lecture. And that is, a construction site is a temporary factory in the field. And they really, really did well at creating this temporary factory in the field and producing, well, 4.5 floors a week. So I want to derive one of our first milestone thoughts. And the first milestone thought I propose to you is that the sheer size of the Empire State Building shouldn't trick us in thinking that it's a particular complex building. Every floor is essentially similar to the one below, even though they taper, which makes things even a bit faster as you go to the upper ones. Maybe you can use some of the workers for that, then to fit out the lower ones. But size is not complexity. Okay, just because it's something big doesn't mean it's particularly complex to build. It just means, in this case, that there's a lot of repetition and we can totally take advantage of that. That makes sense to everybody? All right, here is an even more impressive thing. This is from the same paper as the initial chart, and this is why I wish I had written this paper. What they did is the authors took that supervisor's notebook that I showed you earlier and recreated, re-engineered what the full schedule would have been, because the architecture one simplified it a bit and showed only the main production lines. This is the complete schedule. And I would propose to you that with minor modifications for excavation in the lower floors here, the atrium and such, where there's more and longer things going on, just because the street level floors and the basement floors are so different from the rest, everything else runs at pretty much the exact same clip. This is what really happened to the very best of getting the most detailed schedule for the Empire State Building. I think this is pretty neat, and that teaches us a lot about the power of repetition. So here's our next milestone: identify the repetition. If you want to build something fast, whatever it is, and oh, by the way, what I'm teaching you today is not just applicable to buildings. Maybe you can use this in your own endeavors, whatever you're doing. Maybe you want to write a novel. Well, how do you write a novel? Well, you start maybe by sitting down and saying, I'm going to write 1 page per day, just one. But if you do that over a course of a year, you will have material for an entire novel, would you say? And by the way, not to rub this in here, but you could use this technique maybe if any of you are working on an honors thesis or a master's thesis or a doctoral dissertation. Okay, it's the continuity of repeated small controllable steps that gives the best progress, it seems. Okay, now here's another building, roughly similar era. Which one is this? I know I'm asking a lot of rhetorical questions. Sasha, have you ever seen this building?
Not in person, but I've definitely seen images of it.
Okay, so I suppose you might be from Maryland or one state there, and you don't necessarily commute over the 14th Street Bridge and drive right past it like I used to do.
Correct.
Right. So this one here is, and I love this vintage, mid-century looking postcard view. By now it looks a bit more parking lot and a bit less green, but this is the Department of Defense headquarters of this country. And it's in Arlington. It's not in Washington, D.C., but it's a federal building. So funny thing is they have a D.C. zip code, but it's actually in Virginia proper. Here's a satellite photo. They do have themselves a little nice arena there, helipad, just because, you need to be important. It's adjacent to Arlington National Cemetery and surrounded by 14th Street Bridge that kind of veers off down here on the bottom right. And then one interesting thing is you're starting to really see the structure on this. Do you see, Nick, that this is basically 5 rings with 5 corners. Yes? And you see, Nick, that this is 10 connectors here to get from one outer ring to an inner ring. So there's a whole lot of connectors here. So this building is a very, very uber geometric object. Also in the middle, you see this, Nick? This is probably in the Cold War, this was the world's most well-guarded hot dog booth. Why? Well, it happens to be in the middle of the Pentagon, and the saying goes that at no point was any less than 2 Soviet nuclear missiles pointed at that exact hot dog booth. Okay, well, not because the hot dogs, but because, defense. But nowadays, I hear it's something like a Starbucks, and in summer the employees might get some ice cream there. But so this is the Pentagon. Now we know what the Pentagon looks like. I just want to give you an impression how large this is. On a satellite photo, you might say, yeah, this is a big building. We see the cars next to it. Let's compare with some things we know and some things I hope you know. Empire State Building. This thing is so large that the Empire State Building flipped on its side would just reach across. World's largest oil tanker just reaches across. Queen Mary II doesn't even get across. Nimitz class aircraft carrier, no competition. Airbus A380, my brother happens to work for Airbus Germany, so I'm partial to Airbus and not Boeing. Even the venerable USS Enterprise falls short, which is rather embarrassing considering that it's going to be launched in 2297 or thereabouts. Now, this building has a side length of over 900 feet, 7 floors, 6.5 million square feet, and over 25,000 staff. How fast was this built? It was built in, hold on, I need to move your photos. It was built in basically a year and a half, okay? They built this blazing fast. And mind you, this is still the largest single occupied office building in the world, by far. By far. I mean, look at the Empire State Building for comparisons. It dwarfs it. Now, here is an extra particular view. You were much younger. I remember September 11th when an airplane was crashed into this side. My wife was actually already working in Washington. I was finishing college at the time and we hadn't met yet. And they were just in the middle of a renovation program, which came in fairly helpful because even though this was a massive destruction, they said, we are going to renovate this. And not just renovate, we're going to fix this damage in 1 year. So it was part of a 800 million 10-year renovation project. The entire renovation of the entire Pentagon, the whole thing, was accelerated by 3 years, so they finished it ahead of schedule. And the damage of a wing, which fortunately, I think that was one of the wings where some of the offices had moved out for renovation. So the human toll was thankfully not so bad as it could have been. They basically said, we're going to put a gigantic clock, a countdown timer, like the one that you see on the shuttle launches and rocket launches, you know, the countdown timer. They put that on the construction site facing the building, and they said, we're going to set this to a year and run this down. Weeks, days, minutes, seconds, and we give us 1 year to do this. How did they do this? Well, let's look. This is the original schedule. It's from a company called Hansel Phelps. I happen to know them well. They're kind of local. They specialize in this sort of thing, and they call it SIPS. And that has nothing to do with your favorite sparkly beverage. That is a short interval production schedule. Short interval production schedule in my world just seems to be an upside down repetitive schedule. Why do they do it this way? Well, in the Western world, we are used to read from top to bottom and from left to right. And so this they do first, then they do this, then they do this, then they do this. And you see the secret behind this here, Jessica. You see what their secret is? They color-coded each task. You see the color codings, Jessica, show of them? And each of the contractors, each of the specialty subcontractors that the general contractor Hansel Phelps coordinated, they knew precisely when they needed to be done and when they needed to vacate a particular location. This axis is locations. This pixely thing here says area, 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 area. These are all different locations in the building, and this is time again. And they had to be done. If they weren't done by Friday, I asked them how they did that, and they said Thursday late afternoon, superintendent does a sort of status update. If they are running behind, he notifies them and they work extra hard on Fridays. And if they're not done, they will work through the weekend because by Monday morning they're out, and there's absolutely no way they can overrun that. The contractual penalties and the debt of honor was quite high on this project. So what's the outcome? The outcome is to get it done in a year. And by putting this quite literally, visually in front of everybody and say, this is what we're going to do. And by quite literally putting an enormous digital lit countdown timer on the construction site, they kept everybody on schedule like you haven't seen before. I find this is quite, I mean, as much as tragic as September 11th was, I think this is one of the impressive good things that you know, humans can do if they put their collective minds together. Now, other example, you happen to see mega projects a lot in this presentation. Anybody have heard of the Channel Tunnel? Where's the Channel Tunnel and what channel am I talking about? Benjamin?
Benjamin may not be with us.
Oh, okay.
He was here to set up at the beginning.
Okay. Oh, wait, is Benjamin a staff member?
Yes.
Okay, well, I just elevated him to a student, so sorry for that. I will call on other folks. So this is the English channel or the French channel, depending on which country you're in. And on the left is Great Britain, and on the right is France and the European mainland. And this channel tunnel is 37 kilometers, that is 25 miles or so below the sea level off where the North Sea runs into the Atlantic Ocean, plus approach ramps that are several miles long. And you noticed how they also had to go a bit deeper to be in a very stable rock formation and not be in sediment. They used a total of 11 tunnel boring machines. According to what I've read, they had 13,000 workers, talk about mega projects, and the whole thing cost $21 billion. And I think that is in current US dollars, but doesn't really matter if it's, you know, 1990s US dollars or nowadays US dollars. It's a lot of money. Here's a thought that I want to say. If you look at this channel tunnel, in general, building a tunnel is a really simple thing. You dig a very long hole, okay? That's really all you do. Any specific details are secondary to the overall thing of making progress with digging a hole. Some tunneling is actually a specialty within civil engineering, and there's a number of researchers that study tunnel building. Frankly, I find tunnel building a bit boring because it's basically just one thing. You dig a hole and you keep moving forward digging until you're done. I can think of more exciting work, but the project certainly is an exciting edifice in itself. In fact, it's not just one tunnel. You will see that there's 2 tunnels plus a service and safety tunnel. Why service and safety? Well, first you have trains that go between Britain and France, and they go in both directions, single tracked, running east and west, really, because the tunnel runs, well, kind of like northwest to southeast approximately to go across the channel. And the service tunnel is for maintenance crews and equally important, and it has been used once or twice. If a tunnel fails, if there's a fire, if a train gets stuck, the passenger can escape in a separately ventilated service tunnel, because the worst thing that can happen in a tunnel, whether it's under a mountain or underwater, is fire, and smoke inhalation is the great dangers. And you see here that they also have ventilation systems that are able to move air to keep fresh air there for the occupants should they ever have to leave the train. It's actually one of the 7 wonders of the modern world by our friends and my professional organization, the American Society of Civil Engineers, and we have some old friends there. Channel Tunnel, Empire State Building, here's another one, Panama Canal, Golden Gate Bridge, I'm sure you've heard, CN Tower up in Toronto, and North Sea Protection Works in the Netherlands. Are wonders of the modern world, in addition, Jenny, to the classic wonders of the ancient world that I don't want to embarrass myself trying to count on my 7 fingers right now. Okay, so how did they do this and build this tunnel in, let's see, well, just over 6 years, just six and a quarter years. How did they do this? Well, this is an interesting chart because it tells a very rich story. First of all, Caden, on which side, top, left, right, or bottom, is Great Britain? Just show with a finger, up, down, left, right. Where is Great Britain on this chart?
I could totally be blanking out. I'm not quite sure. I'm looking at it.
You're looking at the upper side. You see all those British sounding Castle Hill, Holywell, Seawall, and there's a dead giveaway. Shakespeare Cliff. Yeah, okay, come on. All right. So Shakespeare Cliff, that horizontal line is the British shore. Okay. And then we are having the other side, Sasha. Do you see Sangat Shaft? Now that sounds awfully French to me, doesn't it? Yeah, okay. So in between, we're seeing something really interesting. If you turn your head sideways for a moment with me, so that you're looking Shakespeare Cliff and Sangat Shaft, and then you're looking from the left to the right. Can everybody do this for a moment? You see that the lines actually branch out. You have lines that go from Shakespeare Cliff to Castle Hill, Holywell, which is getting to the train stations that gets us into London. And a Shakespeare Cliff also gets us to point M, which is the magical midpoint under the tunnel. And Sangat Shaft is equally branching out backward and toward that magical point M. And I don't honestly know what point X is. I can suppose what point M is. Anybody got an idea? Maybe Jenny. What is the magical M behind point M? What does it stand for?
Well, I would think the midpoint of under the channel.
You would think midpoint. I would give you full score for that. And an alternative possibility would be they might call it the meeting point. Okay. It might
to come from if you're tunneling from both sides.
Yes. So here is where we get to see a story. They dug 2 deep round shafts on British soil near the shore and on French soil near the shore. And now this chart is starting to speak for us. Remember the 11 tunnel boring machines? Well, they had 2 to 3 tunnel boring machines going from the British shore toward London, and that's these branches up here. They had the main tunnel boring machines going toward point M. They also had an equal pair of tunnel boring machines and a smaller one for the service shaft coming from Sangat. And lastly, they dug back the approach ramp from where, because trains, railroads can only have 1 to 2% slope. For high-speed trains, it's even slightly less than that. So you need to have a very long, gentle sloped approach ramp to get you under sea level, well under sea level already as you cross the shoreline. Make sense? So now this explains why we have essentially almost a dozen tunnel boring machines. A quick story about the tunnel boring machines. They were there for a very long time. And since they were ending up, since they met, it would have taken how long to dig it with half the tunnel boring machines from one side? Well, it would have taken twice as long, right? So it took half as long because they dug from both sides and met under the channel in the middle. But that caused one problem. It would have been so expensive to dismantle the tunnel boring machines that instead they kind of took a bit of a right turn at point M and buried them there. And to my knowledge, there's a good chance that there's still some tunnel boring machine buried there. They're custom built. Tunnel boring machines get such a lot of wear and tear from tunneling that they might still be there. I have heard one other story that I haven't been able to quite verify, is that Elon Musk bought some tunnel boring machine for one of his, Hyperloop projects and whatnot, and things were actually dug out or revived or refurbished. But generally, tunnel boring machine costs $5 to $10 million, and by the end of building a tunnel of this kind of length, it's barely usable anymore and more scrap metal than machine. Okay. Any comments, thoughts, questions? Do you start to see how this tells us a real story, this otherwise mysterious initially looking chart? Sounds good, Serafina?
Yep.
All right, great. So what do I think we can derive from this? Deriving from this is make consistent progress. We're starting to see similar messages clad in different costumes here. They just planned for the tunnel boring machines to keep digging a few meters a day, 10, maybe 15 foot a day. And they do that for a number of years until they're done. And that is the entirety of building the channel tunnel. Well, of course, there's a whole lot more to it in terms of engineering and safety and structural and building the custom trains and the tunnel boring machines. But on the surface, it's a very simple thing. Have a consistent rate of progress that can be well maintained, that is high enough to make good progress, but not so high that you're starting to take unnecessary risk or that any little challenge during a day will throw you off target and make your project slow down. So give yourself a high, continuous, achievable rate of progress. Now, I did want to quickly touch on a few things that are slightly more into my research field of construction schedules. Here is one of the, Jenny, I'm sure it begs the question now that, well, what did people do for cathedrals? And what did people do for the pyramids? Where's the charts for those? Now, you will not be surprised by now, having heard my interest so far. I tried to look for those, haven't found any yet. Archaeologists are still searching for the ancient construction schedules. There is ancient blueprints, or rather tracings of cathedral elements, full scales, on the wooden drawing floors in the attics of cathedrals, where the stonemasons traced full scale things and built them to size. But those are essentially blueprints or layouts. Those are not schedules. Same thing for Roman temples. I read one archaeology, there's a German researcher whose name I forget, a wonderful archaeologist who has done a lot of thinking just in where are blueprints for Roman and Greek temples, and he actually found a bunch of scratch lines on the plazas in front of Roman temples where they laid out their designs and just chiseled them right in spot and lifted them into place. But sadly, no schedule information yet. So then what is this? This is one of the earliest credited representations of time and, well, things. In this case, it's not tasks or actions or production processes. It is life dates of ancient philosophers, okay? And you see a lot of familiar names. I think Jenny, you will recognize pretty much all of them, I would suppose. Sounds familiar, so I definitely had to put this slide in for you. But here's one interesting thing. You notice that for many of them, we know their life dates. Considering that these folks lived over 2,000 years ago, I find that quite impressive. Next thing is, if you have a few dots, the birth or death of a particular person is not quite sure, but we can estimate when and where they were born. And you know what the craziest story of this is, Adam? Adam, are you there?
Yes.
What, if you look at this chart, what kind of discovery or conclusion can you make if you look at these overlapping life dates, Adam?
Perhaps what philosophers influenced what other philosophers?
They knew each other. They met. They talked with each other. They learned from each other. This is what this chart really says. You know, I have heard a lot of these names, you know, Socrates and one of the more well-known ones, some Aristotle and whatnot. A bunch of them knew each other. Sure, you know, one might have been a teenager and one might have been an old person, but they knew each other. So many of them could have walked the same, you know, garden of philosophers together, and, you know, pupil and teacher. That, I think, is what makes this chart so interesting to me. I just like this, to think that this was a community of people that all interacted in some way or shape. Now, here is the beginnings of how this starts to appear in construction. This is called a bar chart or Gantt chart, after this fellow there, Mr. Henry Lawrence Gantt. He was not a construction person. He was a manufacturing, a factory captain, a early industrialist. And he made these charts. You see that there's these horizontal bars. And these are basically bonus earned, bonus lost. Those are in red. Day work is X, and red X is absent. So he even color-coded the work productivity, the success of individual workers. And interestingly here, still not a schedule, on the left is the names of workers in one of his factories. And what I love about university libraries is, you know, once I found out that there's Henry Lawrence Gantt and he wrote a book with one of the first bar charts, not quite yet a schedule, I went to the university library webpage and requested it. And you know what happened? A few weeks later, I held this book in my hands, a book from over 100 years ago, the original. So I scanned it carefully, put it carefully back in the envelope, and returned it to the library. It's awesome what you can get in the library. This is sort of my detective work that I don't think a lot of my other colleagues are doing. So that got me curious. Where are construction schedules coming from to help us build stuff fast? So the next one I found is from 1915 for the Langwieser Viaduct in Switzerland, which is this beautiful, beautiful, beautiful train bridge there. And so they used the bar chart, not anywhere particularly fast, but then this doesn't have a whole lot of repetition there, so I just got interested in schedules in general. And you see there on the left, that's all sort of German things for, you know, build formwork, insert steel reinforcing and cast concrete and things like that. All right. Next thing, in my detective journey, I took a look at, well, how did schedules develop since then, and are schedules still? I'm trying to trace the story of how did we come from a schedule as fast as the Empire State Building to now? Remember the declining slope? Well, one of the grandfathers of current construction schedules is this gentleman, James Kelly. And James Kelly is a mathematician. He is a mathematician who, after World War II, worked for one of the first private companies to have and use computers. Remington Rand and DuPont corporations put their head together, and he worked with a Dr. Mauchly, co-inventor of the electronic computer at Remington Rand, and then later they made a sort of consulting firm. Now, what did he create? Well, he created this. This holds a very special place near and dear in my heart. You might say, well, that's just some boring old magazine with some cryptic drawing on the cover, but I have this copy in my hands, not here on campus in my desk drawer. And it's one of my treasured scientific belongings. And you know why? It was Jim Kelly's. How is that? Well, Jim Kelly actually spells his name a little unusually, Kelly with EY. Most people ever spell him wrong, poor fellow. So once I got started as a professor, 2005, 2006, I started to read a whole lot of project management journals, got interested in schedules, you know, the good, the bad, the ugly, and the history. And then I started to notice that there was this one letter in a project management magazine from J. Kelly with EY, Elkins Park, Pennsylvania. And I said, huh, that must be the guy, because why, who other Kelly would write about schedules in a project management magazine? So I put together a very friendly letter, looked through the yellow white pages telephone book for an address in Elkins Park, Pennsylvania, and wrote a letter. And you know what happened? He responded. And here is the story of how I, for a very brief time, a few months, was in the touch with the inventor of current scheduling. Well, he said, you know, dear Professor Lucko, thank you so much for writing. I certainly wish you the very best of luck in your scheduling research. Know that I am already long retired. I'm enjoying time with my grandchildren. I never thought I would become something like a construction consultant, being, after all, just a mere mathematician. And he was a very humble fellow. And for a hobby, I nowadays translate the Spanish diaries of Columbus's fourth voyage into English. May you be well, and I hope it will be useful for you that I include a few of my original documents for your interest as I lighten the load on my desk. So that's how I got a copy of Jim Kelly's magazine, where he recounts the origins of scheduling, network scheduling as it's known. And this cover image shows the first network schedule. How did they do that? Well, projects became very complex at that time. And to manage the complexity, they drew networks. And you know how they drew them, Sasha? Do you want to make a wild guess? They drew them by hand on what? If you need a very big piece of paper, what are you going to use, Sasha?
Blueprints?
Wallpaper. They got themselves rolls of plain wallpaper, he told me, and he writes in this article, and they drew these things by hand, and they threw these rolls of wallpaper through the hallway, and they went down on their knees and they drew these things, and that's how current construction schedules emerged. Who would have thought? Okay, so what are network schedules looking nowadays? Well, network schedule nowadays, this is just a complete made-up mock schedule where you have a bunch of tasks. Construction professors love to make a bunch of tasks with random names here, and since no textbook author is terribly creative, this example here happens to just have alphabetic letters, because, you know, you couldn't just come up with names like excavate, build the walls, build the roof. But, you know, this is simple. This is sort of scheduling 101 as I teach it every fall. And you notice that there's some activities that are green and some that are red, right, Jessica? Well, if you look closely at the timings, you will find that there are some times where you have, let's see, 0, 1, 2, 6, plus 4, 10. So these red numbers, and we don't have time to get in the theory right now, but right, Jessica, what schedulers nowadays distinguish that wasn't such a big deal, because remember, all the schedules were just a bunch of slope lines very close together. What schedulers nowadays distinguish is they distinguish schedules into two groups of activities. Critical activities are those that are literally bumper to bumper. If any delay happens, the project will be delayed. Other activities have flexibility in their timing and can shift around and be pushed back a little bit without affecting things. So they color code them red and green. That makes sense, Jessica? Okay, good. That's all I want to say to this. So let's see. The graphical representation is not the most pretty, I have to say. This is a real world construction schedule example. You see the software on the left is sort of a list. It's basically just glorified Excel. On the left, you list things, and on the right, you have a bar chart. Remember, you know, Mr. Gantt, who invented this. This is sort of, you know, the critical and the non-critical activities, and then the arrows is how they depend on each other, you know, like you build the walls before the roof, and therefore you have a dependency link between them. This is how a real construction schedule looks. But I think there's something lost, because I really think that nowadays schedules, they give us more clutter and less big picture. And I'm starting to think that maybe that's a reason. Now, I certainly, you know, have trained myself in that. This is the first schedule when I was precisely your age. I arrived in the US and I took a scheduling lecture, and this is the first schedule I drew. I'm very fond of grid paper, as is most engineers you see there. So this is a network schedule, not on wallpaper, but close. There's a lot of talk about making projects faster nowadays, and I wonder, you see the book here by Murray Wolf. I actually happen to know Murray Wolf, haven't talked with him in quite a while, because he's such an industry practitioner, and he's always too eager and too anxious to get things improved in industry, and you know, research is slow and methodical, and he even had to make faster title for his book here. But here's the thing, it's all network schedules. There is only echoes nowadays of the linear and repetitive schedules that we saw for the Empire State Building and all that. And I think that is a real problem. However, in the German world, in Europe, there is still a bit more memory of that. I was fortunate to briefly have correspondence with Volker Rösch before he passed it away. He wrote a book on Bauprojekt management, which is obviously construction project management. And you notice that he was showing us sloped lines, although not in such a full-fledged way. Most of his book is charts like this. Here's where we currently stand. This is the book from which I learned, and I happen to know Jim Rowings and had him sign my book years after I learned from his book. So this is the current state. Oh, I mean, this book now is 20 years old, but this is the current state of knowledge. You see the green circle thing there, Adam? That is pretty much all that we learn about linear and repetitive schedules now. So there has been, I think, really a decline. There's no example of the Empire State Building. The lines are not really straight. This is sort of a, you know, hodgepodge project that kind of shows how you could plot things, but it tells you barely anything on how to make stuff fast. I think that's a pity. So I looked, was there any other things? You know, I get curious and say, you know, we've talked about networks, which is currently the big thing, because, you know, which things are critical, that means the project manager, Jessica, focuses mostly on them, and then everything else, Jessica, well, it's non-critical, so the project manager can ignore them for the time being, or just, you know, has enough fires to put out on a daily basis of improvising your life on a construction site as it is. Well, there was this thing, line of balance. I will quickly show you how that looks. Line of balance is a technique that, funny enough, is older than network schedules. It came out of World War II, out of the 1940s, and it was, Jenny, how would you pronounce this guy? George Fauch, third line. I have never figured out how to properly pronounce this guy's name.
I don't know. It's one of those names that you know, when
Fouche.
an American
Maybe he
pronounces
was
it,
French, right? Who
yeah,
knows?
Fouche, yeah,
Yeah.
Fouche, I
So,
suppose.
so the funny story is he was sort of low to mid-level, government B in the Pentagon. That's why it fits so well in our story, working for Department of Defense. During World War II, he was sort of involved in that, and then later he was at the Goodyear Tire and Rubber Company, which still exists, race car tires, normal tires, that sort of thing. And there's also a crazy story, the sort of stuff that you find, Jenny, you're gonna love this, but as an amateur historian, just wanting to know, what's the history and reality of schedules. So I look at this guy who has an unpronounceable but distinct name. And I found out, number one, he lived in the 50s and 60s in Northern Virginia. I'm like, hey, that's where I live. I live, just south of Old Town Alexandria. So we might have been walking in the same streets. That's kind of cool. And then I say, oh, and he received some little award for, being a, minor functionary at the Department of Defense. And I'm like, yeah, we have the Pentagon here. I drive by there on a regular basis. And then one of the things that I dig up, completely insane, which I haven't included here to may his memory be preserved positively. At some point in the late 50s or early 60s, he was arrested, appeared in front of a judge, and fined $5 for stealing a bag of groceries at a local Northern Virginia supermarket. I have no idea what was going on. He may have just left his wallet at home or been scatterbrained project planner and forgotten that, but the sort of stuff you find out once you look for names in archives, completely bonkers stuff. Anyway, not the topic of my presentation today, but I guess humans are flawed. This is another success story. This is line of balance. What is line of balance? We'll see what it looks like, but these are cargo ships, and these were two types of cargo ships, Liberty ships and Victory ships. And why were these ships important? Well, during World War II, there was nothing more important than bringing materials, ammunition, and personnel to the main war theater in Europe. And I can tell you that because I'm a German, and as a German, one visits, as a school child, one visits concentration camps. And I'm from the coast in Germany, so I was fortunate to visit a submarine from World War II that is preserved there and is now a Navy memorial from the German side. Interestingly, the German submarines were very, very, very successful at sinking Allied convoys, which were the groups of ships protected by destroyers that brought this over. So these always traveled in packs over the Atlantic. Now, Caden, you see this ship?
Yes, sir.
They mass-produced the Liberty and Victory ships on a scale that has not ever been equaled before or after in history. They built 2,710 Liberty ships on 18 shipyards, both on the east and west coast, in 3 shifts around the clock. And you want to know how much they averaged? You see the ship off the John W. Brown, Caden?
Yes, sir.
Ship like this, month and a half. Okay, month and a half, complete ship. There was another model, slightly different, slightly larger Victory ships that they started a bit later, 534 of them on 6 shipyards in a year. Caden, do you know how big the US Navy is today? The entirety of the US Navy.
No, I do not.
219. They built more ships in a few months than the entire US Navy has today. Granted, there is, a dozen or so aircraft carriers. The ships are vastly more technologically advanced, but and there's reserve fleet. The US Navy has a very large decommissioned mothballed fleet. There are several ghost fleets in large bays, including one here somewhere in the East Coast, where there's a bunch of ships that with a few months notification could be reactivated sort of as a secondary Navy. Not the most modern, but has an engine and knows which way is left or right. But in terms of scale, they built these like, I'm lacking a metaphor here. They built these, they built these things like hotcakes and got them sailing on its way. Here's an actual photo from a single ship. Day 2, lay the keel. Day 6, bulkheads. Day 10, lower deck. Day 14, upper deck. Day 24, launch. And the fastest one, there was some sort of record where they built one ship, and I think it was a publicity stunt where they literally built one of these things in a week and you know, had twice as many people and 3 times as much prefabrication and just riveted this thing together. Similarly, for the war effort, they also built jeeps. You know, jeeps, these you know, very plain little cars. You know, basically a box with 4 wheels that still exist. Well, nowadays it's the Humvees. The civilian version is the Hummer, which nobody needs. Least of all Arnold Schwarzenegger, I should say. But they build a lot of these and they use the same principles. How do they do that? Well, here, Caden, is a line of balance. And this makes me feel a bit more at home again with how to build stuff fast. There's actually 3 steps, and funny enough, it's you read the bottom, then the left, and then the right. How do you read this? On the bottom, you read an assembly tree, and you see the yellow dot, Caden?
Yes, sir.
That's the finished ship. I'm simplifying this, but you see that then, you know, there's, let's say, you know, the lower decks and the upper decks, and each of them has components. And you work backward. You see how the schedule here goes backward from the delivery date, Caden? So that is an interesting thing. That's the first time we see that. So I find that a really interesting thing. If you have a hard deadline, you work backward when you need to start to meet that deadline at time 0. That's like the clock countdown timer at the Pentagon. Then over here is the delivery schedule. This is how many ships you need to deliver each month. The black is the plan, the red is the actual, and you know, currently the actual seems to lag behind. This is such an interesting method that because this method allows us to identify why are we lagging behind the deliveries of all these units. Well, all of these points, Sasha, you see these merge points here that are numbered merge points?
Yes, sir.
So each of these merge points is essentially a checkpoint. And what you do is you count how much has flown through each of these checkpoints, and you plot that, and you could see, oh, we're behind. Why? We're behind on deliveries. Well, 10 and 11 seem to be slow. Is it 8 or 9? Oh, 9 is fine. It's 8. So it's this branch. Is it 7 that's slow? Yes, it is. Well, is it 6 or 4? It's 4. 6 is fine. So, Sasha, in just a few moments, you see how we have identified that this inflow is a problem, and we need to focus our managerial attention on that.
Mm-hmm.
Okay, so that's a pretty good thing of having production flow, and I don't think I've seen much of that before. I don't think I've seen much of that before or after since. Now I need to see that I move a few slides because we're running short on time, because I'm having such a good time and I don't want to unnecessarily tax your time attention. So one could say that I'm leading a bit of a resurgence, and the resurgence is I'm trying to propose that we should look at schedules like this. This is work over time, and this we're now very familiar with. I find these networks very confusing. There's a wonderful quote in the literature that literally says, if these networks get too large, because mind you, in construction projects, a real project takes anywhere from 1 to 2 years. Give you an example, Monroe Street Market. You all know Monroe Street Market. It's right across from campus and it holds Potbelly, super important, and Barnes & Noble, still very important, right? And that's your typical, 5-story, 2-3 blocks of multiple mixed use. That means commercial on the ground floor and residential on the upper floor, inner city block, and 2 years and 1,500 to 1,800 activities in a network schedule. That's a lot. That's a lot to coordinate. And I think, and I'm trying to slowly convince, I'm actually working with a contractor from Monroe Market. I'm trying to tell them, if you have 1,800 of these things, you can't see them all. Here, everything that's similar get lumped together and starts to trace, you see this, Nick? It starts to trace trajectories. This could be dozens of tasks that you're doing, but they all trace a trajectory. So this is literally an entire schedule for an entire project, could be 2-3 years long, on one page. I think there's a great value to see the big picture, and I think, and my current research quite strongly focuses on my proposition that I think that we're focusing way too much on the details and not enough on the big picture. In the interest of time, I'm going to skip, my research slides. I got too excited with the, the grand story, and I will cut out my more theoretical research to lest I rob you time and put you to sleep. So I want to leave you with a couple of thoughts on how to build stuff fast, and that is, mind you, after you pack your towel for the Hitchhiker's Ride Through the Galaxy. If you don't get that cultural reference, go read Douglas Adams. So what have we learned? Size is not necessarily complexity. What matters is that we find the repetition and really focus on what is the overall goal of all this repetition. Details come second. This is sort of the same message in a different costume. Details matter. I'm a very detail-oriented person by nature. Engineers are, but as engineers, as project planners, and I would say in general, it is a good thing if you manage to stay focused on the outcome while sweating the details at the same time. But they are in that order and not the other way around. And last not least, the constant drop hollows the stone. No, what is this saying in English? Did I retranslate that from German, or is that something that actually made sense what I just said?
That completely makes sense.
Okay, so if you ever go to a cave and you look at these magnificent stalactites and stalagmites, and you know how you do stalactites and stalagmites, how you remember which one is which? Do you know that story? Stalactites are like the letter T, they hang from the ceiling. Stalagmites are like the letter M, they come from the bottom. Did you know that? Now you do. You will never confuse them again. They grow over tens of thousands of years with one drip at a time that evaporates and leaves a minuscule amount of calcium, and it builds tens of feet tall, tens of tons heavy things. It works. It works. Nature shows the way. And speaking of nature, this photo is one of my favorite photos from actually conference. I was fortunate enough to go to a Construction Research Congress in the Canadian Rocky Mountains, and I looked at this mountain and I said, that is complexity. That's Mother Nature. We haven't been able to copy or imitate or even get anywhere close with what we're doing. But thankfully, as humans, we don't need to. We can focus on simple, organized, systematic things and marvel at Mother Nature's works. And with that, I am, well, slightly over time. Shame on me as a scheduling professor, but I hope you forgive me. Totally, I was precisely 1 hour because Jenny took 5 minutes in the beginning. So thank you for that, and I'm open to comments, thoughts, questions.